The instant is not in time. Time is in the instant. How often have you heard the phrase, an instant in time? At one instant. A stitch in time saves nine. It all happened in an instant. But the instant is not in time. Time is in the instant. I'm quoting there the phrasing of Julian Barber, an independent physicist who works on the physics of time. He wrote a book, The End of Time, where he argues time is an illusion. I read this in what I called in the last episode the interglacial period between the fabric of reality and the beginning of infinity. Welcome to the Talkcast, where we're at episode 2 of my discussion of the fabric of reality, chapter 11, Time, the first quantum concept. Last episode, the fabric of reality talked about how the flow of time is itself an illusion. We don't actually experience any flow of time, although we think we do. And certainly physics reifies this idea that there is no such flow of time. So that is all a mistake. David goes on to say, and I'm picking this up now on page 264 of the fabric of reality, and he writes, quote, "The origin of this sort of mistake is that we are accustomed to time being a framework exterior to any physical entity we may be considering. We are used to imagining any physical object as potentially changing, and so existing as a sequence of versions of itself at different moments. But the sequence of moments itself, in pictures like figures 11.1 to 11.3, is an exceptional entity. It does not exist within the framework of time. It is the framework of time." End quote. And that's worth repeating. It is the framework of time. What is this framework of time? Well, let's paraphrase what David had just said there. The framework of time is an object existing as a sequence of versions of itself at different moments. But the sequence of moments itself is an entity. End quote. So it's the sequence of moments, the sequence of change. That's the framework of time. But as we'll come to see, time itself is not that simple, even if we can describe what this framework is. Skipping a little, and then David goes on to say, quote, "No accurate picture of the framework of time can be a moving or changing picture. It must be static. But there is an inherent psychological difficulty in taking this on board. Although the picture is static, we cannot understand it statically. It shows a sequence of moments simultaneously on the page, and in order to relate that to our experience, the focus of our attention must move along the sequence." End quote. So in other words, we have a sequence of pictures in a diagram that tries to picture what's going on with time, but all of those are misleading in some way. You cannot speak in such a way as to not be misunderstood. One may as well say you cannot picture things in such a way as to not be misunderstood. All language is ambiguous, David has said. All diagrams are misleading in some way as well. We can't get perfect clarity, but here we just can't picture what's going on with time at all. Skipping yet another paragraph, and David goes on to say, quote, "But there is more to this problem than the difficulty of illustrating the common sense theory of time. The theory itself contains a substantive and deep equivocation. It cannot make up its mind whether the present is, objectively, a single moment or many, and hence, for example, whether figure 11.1 depicts one moment or many. Common sense wants the present to be a single moment so as to allow the flow of time, to allow the present to sweep through the moments from past to future. But common sense also wants time to be a sequence of moments, with all motion and change consisting of differences between the versions of an entity at different moments. And that means that the moments are themselves unchanging. So a particular moment cannot become the present or cease to be the present, for these would be changes. Therefore, the present cannot objectively be a single moment." End quote. Let's just say that again. The present cannot objectively be a single moment. End quote. Well, it might seem that way to you, that the present is a single moment, but that's just a subjective feeling you have. It's not objectively anything to do with the truth of the matter. And objectively, the truth of the matter, or our best explanation of the matter, comes to us not from our subjective feelings or our subjective experiences, but rather from our good explanations, which deny this flow of time and which deny this idea of there being a single preferred moment. Of course, none of this is to solve the question of consciousness and what consciousness is and why it seems to be always located at a particular place. But David is saying, well, consciousness is located at all these places. So the person in the past is still really there, experiencing something. And the person in the future is there experiencing something. But, of course, we are neither the person in the past or the person in the future. We are a person occupying some particular time, subjectively. And what David has said there in that paragraph that I've just read is that there is change, subjectively, but nothing is changing objectively from the universe, or multiverse if you prefer, point of view, from that perspective, from the physics perspective. It's all just there. This is another inherent psychological difficulty people have, in large part because the future is open-ended due to knowledge creation, which, on my account, is what free will is. But at the same time, physics is sovereign. And so the laws of physics determine what happens next, but they also mandate that what happens next is inherently unpredictable because of the differentiation of fungible instances of particles. For more on that, see my Multiverse series. It's too much to go into right now. Or just pick up your copy of The Beginning of Infinity and search for the word fungible, especially if you've got the electronic copy or something on Kindle, something like that. Fungible is talked about in chapter 11. Anyway, the point is that the laws of physics determine that what happens subjectively is unpredictable because knowledge creation is inherently unpredictable. And that comes down to you don't know subjectively what universe you're going to be in when differentiation of the universes occur. If you're performing an interference experiment, you don't know what's going to happen next. That's the reductive explanation of what's going on. But at the emergent level, you can't predict the growth of knowledge. And that, to me, is another way of just saying we have free will. It's the parsimonious way of explaining what free will is. It's fundamentally to do with knowledge creation. But let's not go into that now. I've got all these resources that you can look at. David goes on to say, quote, "The reason why we cling to these two incompatible concepts, the moving present and the sequence of unchanging moments, is that we need them both, or rather, that we think that we do. We continually invoke both of them in everyday life, albeit never quite in the same breath. When we are describing events, saying when things happen, we think in terms of a sequence of unchanging moments. When we are explaining events as causes and effects of each other, we think in terms of the moving present." End quote. So that's a cool distinction there between describing, in other words, just saying what happens and when, versus explaining, saying what happens in terms of causes and their effects. David goes on, quote, "For example, in saying that Faraday discovered electromagnetic induction in 1831, we are assigning that event to a certain range of moments. That is, we are specifying on which set of snapshots in the long sheaf of snapshots of world history that discovery is to be found. No flow of time is involved when we say when something happened, any more than a flow of distance is involved if we say where it happened. But as soon as we say why something happened, we invoke the flow of time. If we say that we owe our electric motors and dynamos in part to Faraday, and that the repercussions of his discovery are being felt to this day, we have in mind a picture of the repercussions beginning in 1831 and sweeping consecutively through all the moments of the rest of the 19th century, and then reaching the 20th century and causing things like power stations to come into existence there. If we are not careful, we think of the 20th century as initially not yet affected by the momentous event of 1831 and then being changed by the repercussions as they sweep past on their way to the 21st century and beyond. But usually we are careful, and we avoid that incoherent thought by never using the two parts of the common sense theory of time simultaneously. Only when we think about time itself do we do that, and then we marvel at the mystery of it all. Perhaps paradox is a better word than mystery, for we have here a blatant conflict between two apparently self-evident ideas. They cannot both be true. We shall see that neither is true." End quote. There's David using a technique he often does. Both sides are wrong. Many people love this particular technique. We can trace it to Karl Popper, who also employed it skillfully throughout his writings as well. It's unsurprising, therefore, that someone who is strongly influenced by the work of Popper would use Popper's particular technique. Popper's often persistent promoter effectively researches, or Popper's only prominent public expert, really. No, not really. You'll notice there that those last two sentences were completely shoehorned into this discussion. I was just having fun trying to make an acronym of Popper, Popper, that applied to David. I tried to cheat and get ChatGPT-4 to do it. It was completely hopeless, truly hopeless. No matter how I phrased the prompt, it came up with acronyms about researchers and promoters, but everything else was rubbish. It couldn't understand what I wanted. Back to time, or I'm going to run out of it, of course. David goes on to say, quote, "Our theories of physics are, unlike common sense, coherent. And they first achieved this by dropping the idea of the flow of time. Admittedly, physicists talk about the flow of time, just as everyone else does. For example, in his book Principia, in which he set out the principles of Newtonian mechanics and gravitation, Newton wrote, 'Absolute true and mathematical time of itself and from its own nature flows equably and without relation to anything external.'" End quote from Newton. David goes on, "But Newton wisely makes no attempt to translate his assertion that time flows into mathematical form or to derive any conclusion from it. None of Newton's physical theories refers to the flow of time, nor has any subsequent physical theory referred to or been compatible with the flow of time." End quote. And I'm skipping a few paragraphs here. David goes on to explain why Newton used the word flow and explains why Newton was likely using it in the same way that we speak of the sun rising. But read the actual book for more on this. I'll skip that entire section and pick it up where he writes, quote, "I have been drawing successive moments separated from one another. But in all pre-quantum physics, that is an approximation because time is a continuum. We must imagine infinitely many, infinitely thin snapshots interpolating continuously between the ones I have drawn. If each snapshot represents everything throughout the whole of space, that physics exists at a particular moment, then we can think of the snapshots as being glued together at their faces to form a single unchangeable block containing everything that happens in space and time." Figure 11.4. That is the whole of physical reality. An inevitable shortcoming of this sort of diagram is that the snapshots of space at each moment are shown as being two-dimensional, whereas in reality they are three-dimensional. Each one of them is space at a particular moment, thus we are treating time as a fourth dimension, analogous to the three dimensions of space in classical geometry. Space and time considered together like this as a four-dimensional entity are called spacetime. In Newtonian physics, this four-dimensional geometrical interpretation of time was optional, but under Einstein's theory of relativity it became an indispensable part of the theory. That is because, according to relativity, observers moving at different velocities do not agree about which events are simultaneous. End quote. And if you saw my last episode or listened to my last episode, you will know that there I provided a proof of what is called the relativity of simultaneity. So I won't go into more of that here and now. By now I mean now in your reference frame, not mine, which happened elsewhere and earlier. That's a joke, of course. But let's also see what Sam Kuyper says about this in his paper on some of this. His paper is titled, I have a printout of it here, "The Quantum Theory of Time, a Calculus for Q Numbers." And he talks about the quantum theory of time. So I'm not going to go into much of that here and now. We'll save that for a subsequent episode. But he does go into, to set the scene, some of the differences between Q number, quantum number time, so-called time, and C number time, which is the time that Newton is talking about and the kind of time that is required for space-time physics as well. The upshot of what Sam Kuyper is doing in his paper is to riff upon and to extend what Paige Wooters has done. We'll get to that eventually, not in this episode. But he also talks about this classical time, the C number time. And he says of this, following Newton, that C number time flows independently of the behavior of quantum systems and should not be confused with clock time. End quote. So in other words, clock time is how you measure time. And all clocks are physical objects, and so therefore the increment on a clock is a physical thing, a physical change that actually occurs. And so because all clocks are physical, they're governed by the laws of physics, which are the quantum laws of physics. So the way in which time is marked, therefore, and is measured, is on clocks. And so, as Sam goes on to say, To make clear the distinction between clock time and C-number time, consider a hypothetical situation in which all physical systems in the universe suddenly freeze relative to C-number time. Clocks are physical systems and will be stationary during this freeze, which makes the freeze and its duration completely undetectable to any observer in the universe. End quote. The only kind of time that's real is physical time. And the only physical time is Q-number time, not C-number time. Not the time that is explained by Newton and not the time that is explained in space-time physics, Einstein's theory. We will get into that distinction later in a subsequent episode, and as I keep promising, we will talk to Sam about this as well. For now, let's keep on going with what David has to say in The Fabric of Reality about all this, and I'll pick it up after skipping quite a number of paragraphs, and he says, quote, "As I have said, we think of the flow of time in connection with causes and effects. We think of causes as preceding their effects. We imagine the moving present arriving at causes before it arrives at their effects, and we imagine the effects flowing forward with the present moment. Philosophically, the most important cause and effect processes are our conscious decisions and consequent actions. The common sense view is that we have free will, that we are sometimes in a position to affect future events, such as the motion of our own bodies, in any one of several possible ways, and to choose which shall occur, whereas in contrast, we are never in a position to affect the past at all. I shall discuss free will in chapter 13. The past is fixed, the future is open. To many philosophers, the flow of time is the process in which the open future becomes moment by moment the fixed past. Others say that the alternative events at each moment in the future are possibilities, and the flow of time is the process by which moment by moment, one of those possibilities becomes actual, so that, according to those people, the future does not exist at all until the flow of time hits it and turns it into the past. But if the future really is open, and it is, then that can have nothing to do with the flow of time, for there is no flow of time. In space-time physics, which is effectively all pre-quantum physics starting with Newton, the future is not open. It is there, with definite fixed contents, just like the past and present. If a particular moment in space-time were open in any sense, it would necessarily remain open when it became the present and the past, for moments cannot change, end quote. So there David has talked about free will. Now, we must say, and we'll have more to say about this in chapter 13, that David has said that his perspective on free will has somewhat changed from this. Namely, he said that free will is a high-level explanatory concept and does not require the multiverse as a fundamental part of its explanation. Also, I guess constructor theory will form a part of that change in perspective as well. Let's see, in fact, what lead researcher on constructor theory, Chiara Marletto, has to say on this in the first book-length treatment of constructor theory, The Science of Can and Can't. I will just pick up my book from over here and open up at a page that I've prepared earlier. This is from page 63, and Marletto writes, quote, "The dynamical law's sequence of events fixes everything. It is given once and for all. All your ideas are laid out there. There seems to be no room for them to be unpredictable, as they should be if they were truly free choices. We have just outlined what is called a deterministic nightmare. The fact that there does not seem to be any room for free choice if one presupposes the existence of a fixed predetermined story for our universe, which is the picture that the traditional conception of physics in terms of dynamical laws and initial conditions seems to suggest. For example, whether tomorrow you will have croissants or kippers for breakfast has been fixed at the start of the universe in its initial conditions. The same goes for the fact that you are reading this text right now, instead of some other book, or maybe doing something else altogether, such as watching your favorite TV show, all determined at the beginning of the universe down to the precise words, typos included. Unpredictability of action or free will is therefore another counterfactual that the dynamical law approach does not seem to be able to accommodate. We do not yet know how to accommodate exactly free will in physics, but that only means we will have to think harder. The problem exists, but it is not insoluble. It only appears to be so if contemplated from the narrow dynamical law type of approach." End quote. And brilliant. Okay, that's comforting to me because I endorse a perspective on free will. And I defend free will and I explain free will quite often because I want to understand this stuff. I want to understand how choice is real. I want to understand how knowledge creation is inherently unpredictable. And I think a parsimonious way of doing that is free will. And when people say it's ruled out by determinism, that's an excellent explanation as to why. It's only ruled out by determinism on the assumption that the dynamical laws approach is the most valid or only valid way of looking at how physics determines what happens in the universe. If it's a science of can and can't, if it's science of what can happen and what can't happen, then it opens up the possibility of humans making choices. Choices not determined necessarily by dynamical laws in the same way that people think they're determined. In essence, they may be determined in such a way, as I've already indicated in this very episode, to be unpredictable, inherently unpredictable. If it's inherently unpredictable, then it leaves open choice. It leaves open the future. And David Deutsch has said the future really is open. Now, in what sense is it really open? Because people can create knowledge, and they can choose to create knowledge or choose not to create knowledge. And it makes no sense. It's fundamentally incoherent to say that the knowledge that is created is in some sense there in its antecedents, the things that have gone before in human history. That, Neanderthals or the ancient, prehistoric ancestors of human beings bashing rocks together because they're using them as tools or whatever, in some sense contain the knowledge, ultimately speaking, that's there in the iPhone, that is there instantiated in the iPhone, because the bashing of the rocks leads to more complicated constructions using rocks, which leads to more complicated tools, which eventually, via this long chain of causation, leads to the tools that are used to make the iPhone and leads to the iPhone. That makes no sense. But saying that in some way all of our ideas are determined by the existence of previous ideas is inherently incoherent. But we're getting away from time. So let's go back to time, and let's go back to what Chiara has said in one of her professional papers on this, and her collaborator Marletto and Vedral have said in their 2016 paper, which is titled Evolution Without Evolution and Without Ambiguities. What they say in this paper, among other things, and I'll just be reading an excerpt here from Marletto and Vedral now. Quote, "All dynamical laws are affected by a deep problem. They are formulated in terms of an extrinsic parameter, time, which is not itself an element of dynamics, and hence it is left unexplained. One powerful way of addressing this problem is the timeless approach to time. Its logic is elegant. Both dynamics and time should emerge from more fundamental elements chosen so that the dynamics satisfies certain criteria." End quote. And I'm skipping a whole bunch of their paper, and I'm just picking it up at the solution. And they say, quote, "Quantum theory provides the means to solve the problem of time via its most profound properties, having pairs of non-commutable observables and permitting entanglement between subsystems of the universe. Unlike in classical dynamics, there is no need to assume any underlying motion. Both time and motion are explained in terms of motionless entanglement contained in the state of the universe. This elegant model, leading to an evolution without evolution, has promising features such as its compatibility with quantum gravity." End quote. So we don't have a theory of quantum gravity yet, of course, but this helps constrain or inform future theories of quantum gravity if they come, or when they come, one might say. Of course, the idea that gravity will be quantized in some way is itself a speculation. We don't know. There could be an entirely different third theory that does who knows what. We cannot predict the content of future theories. Marletto and Vedral go on to say, and they're going to invoke the Page-Wooters idea as Kuyper's does, and that's what informs David Deutsch's perspective here in the fabric of reality as well. We won't get there until the next episode of Topcast, but here we'll get to it now just to talk about this particular peer-reviewed paper, so to speak, that Marletto and Vedral have, because they talk about the flow of time. And we've talked about the flow of time here. David's talked about the flow of time. And they've said in a section titled The Appearance of the Flow of Time, quote, "It is worth pointing out that there is no flow of time in the Page-Wooters picture. The Page-Wooters approach shows that the Schrödinger equation holds for the rest of the universe. But the flow of time has to emerge as a result of there being subsystems of the rest of the universe that can perform measurements and store their results, thus constructing a history." skipping pages and pages of this, and they have another section titled The Arrow of Time, where they say, quote, "In the page Wooters picture, there is no arrow of time, just like in unitary quantum theory. The page Wooters approach gives rise to a time reversal symmetric dynamical law. Thus, the arrow of time has to be imposed by a separate postulate, requiring that under that dynamical law, a given monotone always increases or decreases. Thus, the arrow of time has to be imposed by a separate postulate," end quote. So there is no arrow of time. Fundamentally, it has to be imposed by a separate assumption. You just assume there is this thing called the arrow of time. But if you use quantum theory, this particular way of understanding quantum theory, the place of time in quantum theory, how to understand time in quantum theory, via the Page-Wooters instruction, which is, as I say, fundamentally what is informing the fabric of reality perspective on this, then what you get are time-symmetric laws. Now, this is unlike in thermodynamics, where you have laws that are not time symmetric, namely the second law of thermodynamics. But it's suggesting here that, well, quantum theory has to be deeper than the laws of thermodynamics. And Marletto has written on, by the way, the laws of thermodynamics and how they can be understood in terms of constructor theory. So that's well worth reading, that particular paper. And I might break that paper down at some point as well. They conclude their paper with, quote, "We have shown that the Page-Wooters timeless approach to time in quantum theory has no ambiguities, thus vindicating it as a viable proposal for the emergence of time in a timeless universe described by the Unitary quantum theory," end quote. This unitary quantum theory is something that Sam Kuyper has written extensively about. In fact, his thesis was about this, and it's available online. And he talks about how Everettian quantum theory, the relative state quantum theory, is one version of unitary quantum theory. That the system, the universe, the multiverse evolves according to the Schrödinger wave equation, among other things, the other things being the Heisenberg picture is another way of looking at this. Kuyper talks about this in his thesis. Again, when I talk to him, it'll be well worth talking to him about unitary quantum theory. Kuyper talks about this in his thesis. As I say, we'll come back to the Page-Wooters construction in the next episode. David goes on to write in The Fabric of Reality, quote, "Subjectively, the future of a given observer may be said to be open from that observer's point of view, because one cannot measure or observe one's own future. But openness in that subjective sense does not allow choices. If you have a ticket for last week's lottery, but have not yet found out whether you have won, the outcome is still open from your point of view, even though objectively it is fixed," end quote. So, subjectively, things are unpredictable. And this means both for you and also, in general, everyone else on Earth in general. So forget lottery tickets. Talk about the growth of knowledge. The growth of knowledge is inherently unpredictable. And I've argued in various places, like, as I say, here and here and here, among other places, that free will is a consequence of knowledge creation and also emerges as a simple thing of the complex interaction between fundamental particles, rather like cats do or people do in general. That's the whole idea of emergence, the emergent simplicity of something from what's going on at a deeper level, which is the complex motion of particles, let's say. Let's skip a few paragraphs and I'll pick it up where David goes on to say, quote, "To be an effect of some cause means to be affected by that cause, to be changed by it. Thus, when space-time physics denies the reality of the flow of time, it logically cannot accommodate the common sense notions of cause and effect either. For in the block universe, nothing is changeable. One part of space-time can no more change another than one part of a fixed three-dimensional object can change another," end quote. So what's he talking about here? Well, he's coming to the idea that space-time physics is just not correct. It's not true. It doesn't fit with the quantum theory of time that we're going to get from Page and Wooters. Skipping more, and he says, quote, "The laws of physics that determine one snapshot from another are the glue that holds the snapshots together as a space-time. Let us imagine ourselves magically and impossibly outside space-time and therefore in an external time of our own, independent of that within space-time. Let us slice up space-time into snapshots of space at each moment as perceived by a particular observer within space-time. Then shuffle the snapshots and glue them together again in a new order. Could we tell from the outside that this is not the real space-time? Almost certainly. For one thing, in the shuffled spacetime, physical processes would not be continuous. Objects would instantly cease to exist at one point and reappear at another. Second, and more important, the laws of physics would no longer hold. At least the real laws of physics would no longer hold. There would exist a different set of laws that took the shuffling into account explicitly or implicitly and correctly described the shuffled spacetime. End quote. Yes, what physical laws are about are regularities in nature. If you shuffle up these space-time snapshots, then you don't have regularities in the same way. You wouldn't have these causes preceding their effects, these sequences of cause and effect, what one might say are logical sequences of causes and effects. You wouldn't have regularities. It would be very difficult to come up with other emergent regularities in nature as well. Chemical equations and chemical laws and chemical reactions, that kind of thing. Geological laws and biological ones as well. The whole theory of evolution would fall apart because you wouldn't be seeing increased complexity or anything like that. You wouldn't be seeing that mutations are going on to be selected for. It would be a mess. There would be physical laws that would have to govern the reordering of the snapshots. After all, something's going on there, and there has to be some law of physics that describe the shuffling, but it wouldn't be a regularity in nature. It would be randomness in nature. I'll pick it up after David goes through the argument about why it's meaningless and just say, quote, "In terms of real physics, physics as perceived by the space-time inhabitants, all this slicing up and regluing of space-time is meaningless. Not only the shuffled space-time, but even the collection of unglued together snapshots is physically identical to the original space-time. We picture all the snapshots glued together in the right order because this represents the relationships between them that are determined by the laws of physics. A picture of them glued together in a different order would represent the same physical events, the same history, but would somewhat misrepresent the relationships between those events. So the snapshots have an intrinsic order defined by their contents and by the real laws of physics. Any one of the snapshots, together with the laws of physics, not only determines what all the others are, it determines their order and it determines its own place in the sequence. In other words, each snapshot has a time stamp encoded in its physical contents." End quote. In other words, there's a logic to the way in which these things are organized, these snapshots are organized. But if you have the laws of physics, if you independently know what the laws of physics are, then you're going to be able to figure out what the order should have been. David goes on to say, quote, "We can reconstitute the space-time by using the intrinsic order determined by the laws of physics. We start with any of the snapshots. Then we calculate what the immediately preceding and following snapshots should look like, and we locate those snapshots from the remaining collection and glue them together on any side of the original snapshot. Repeating the process builds up the whole space-time. These calculations are too complex to perform in real life, but they are legitimate in a thought experiment in which we imagine ourselves to be detached from the real physical world. Also, strictly speaking, in pre-quantum physics, there would be a continuous infinity of snapshots, so the process just described would have to be replaced by a limiting process in which the space-time is assembled in an infinite number of steps. But the principle is the same. The predictability of one event from another does not imply that those events are cause and effect. For example, the theory of electrodynamics says that all electrons carry the same charge. Therefore, using that theory, we can, and frequently do, predict the outcome of a measurement on one electron from the outcome of a measurement on another. But neither outcome was caused by the other. In fact, as far as we know, the value of the charge on an electron was not caused by any physical process. Perhaps it is caused by the laws of physics themselves, though the laws of physics as we currently know them do not predict the charge on an electron. They merely say that all electrons have the same charge. But in any case, here is an example of events, outcomes of measurements on electrons that are predictable from one another, but make no causal contribution to one another. End quote. Yes, the charge on an electron, like any number of constants of nature, why those values? Well, it's an open question. Okay, so we need some deeper laws of physics, I guess, in order to predict what these numbers are. And there are many different theories that vie for this so-called fine-tuning issue, why the constants have the value that they do. There must be some explanation. We don't have one yet. David goes on to say, quote, "Here is another example. If we observe where one piece of a fully assembled jigsaw puzzle is, and we know the shapes of all the pieces, and that they are interlocked in the proper way, we can predict where all the other pieces are. But that does not mean that the other pieces were caused to be where they are by the piece we observed being where it is. Whether such causation is involved depends on how the jigsaw puzzle as a whole got there. If the piece we observed was laid down first, then it was indeed among the causes of the other pieces being where they are. If any other piece was laid down first, then the position of the piece we observed was an effect of that, not a cause. But if the puzzle was created by a single stroke of a jigsaw puzzle-shaped cutter and has never been disassembled, then none of the positions of the pieces are causes or effects of each other. They were not assembled in any order, but were created simultaneously in positions such that the rules of the puzzle were already obeyed, which made those positions mutually predictable. Nevertheless, none of them caused the others, end quote. This, it would seem, is constructor theory in nascent form. It talks about how you can have the appearance of cause and effect, but in fact, it just tells you which of the puzzle pieces are possible and impossible in terms of their relations to others. Although, if you had this puzzle cutter just coming down on top of what amounts to being physical reality, the jigsaw puzzle, then none of what happens is occurring in the puzzle, so to speak, are causes and effects of the other things. The cause and effect is an emergent thing that you have to explain in terms of an underlying principle about what's going on, or an underlying law about what's going on. You need to know something further. In terms of the puzzle, is it that you put down one piece first, and then the next piece is determined by that, and the surrounding pieces are determined by that, and so on and so forth? Or were all of them created simultaneously and they've never been disassembled? We don't know. We don't know. We're in the position of not knowing why causes and effects are the way they are, but we just know that they happen, but we don't have the underlying explanation. They emerge from deeper physical laws. In any case, David goes on to say, quote, "The determinism of physical laws about events in space-time is like the predictability of a correctly interlocking jigsaw puzzle. The laws of physics determine what happens at one moment from what happens at another, just as the rules of the jigsaw puzzle determine the positions of some pieces from those of others. But just as with the jigsaw puzzle, whether the events at different moments cause one another or not depends on how the moments got there. We cannot tell by looking at a jigsaw puzzle whether it got there by being laid down one piece at a time. But with space-time, we know that it does not make sense for one moment to be laid down after another, for that would be the flow of time. Therefore, we know that even though some events can be predicted from others, no event in space-time caused another. Let me stress again that this is all according to pre-quantum systems, in which everything that happens in space-time. What we are saying is that space-time is incompatible with the existence of cause and effect. It is not that people are mistaken when they say that certain physical events are causes and effects of one another. It is just that that intuition is incompatible with the laws of space-time physics. But that is all right, because space-time physics is false. End quote. A classic David Deutsch moment in this book, where he sets up some inconsistency with some well-known common sense theory, or with some good explanation in physics, but he says, but that's okay that this inconsistency exists out there because it's false anyway. Common sense is false. This common sense explanation is false. This particular explanation happens to be false, even if it's physics. So now I'm skipping a couple of pages and I'm going to pick it up where David says, quote, "We are forced to conclude that in space-time physics, conditional statements whose premise is false, if Faraday had died in 1830, have no meaning. Logicians call such statements counterfactual conditionals, and their status is a traditional paradox." End quote. We'll pick it up again very shortly. Again, this really is setting the groundwork for, and is prescient of, constructor theory, which is really a theory of counterfactuals, more than it's a theory of constructors. But you have to call it something. Counterfactual theory doesn't sound as cool, I don't think. Perhaps that's one reason. David goes on, quote, "We all know what such statements mean, yet as soon as we try to state their meaning clearly, it seems to evaporate. The source of this paradox is not in logic or linguistics, it is in physics, in the false physics of space-time. Physical reality is not a space-time. It is a much bigger and more diverse entity, the multiverse. To a first approximation, the multiverse is like a very large number of coexisting and slightly interacting spacetimes. If spacetime is like a stack of snapshots, each snapshot being the whole of space at one moment, then the multiverse is like a vast collection of such stacks. Even this, as we shall see, slightly inaccurate picture of the multiverse can already accommodate causes and effects. For in the multiverse, there are almost certainly some universes in which Faraday died in 1830, and it is a matter of fact, not an observable fact, but an objective fact nonetheless, whether technological progress in those universes was or was not delayed relative to our own. There is nothing arbitrary about which variants of our universe the counterfactual, if Faraday had died in 1830, refers to. It refers to the variants which really occur somewhere in the multiverse. This is what resolves the ambiguity. Appealing to imaginary universes does not work because we can imagine any universes we like, in any proportions we like. But in the multiverse, universes are present in definite proportions. So it is meaningful to say that certain types of event are very rare or very common in the multiverse, and that some events follow others in most cases. Most logically possible universes are not present at all. For example, there are no universes in which the charge on an electron is different from that in our universe, or in which the laws of quantum mechanics do not hold. The laws of physics that are implicitly referred to in the counterfactual are the laws that are actually obeyed in other universes, namely the laws of quantum theory. Therefore, the if-then statement can unambiguously be taken to mean in most universes in which Faraday died in 1830, technological progress was delayed relative to our own. In general, we may say that an event X causes an event Y in our universe if both X and Y occur in the universe, but in most variants of our universe in which X does not happen, Y does not happen either. End quote. This is a wonderful example of why constructor theory is almost like a generalization of quantum theory, which is generalized already in the theory of quantum computation, and so constructor theory takes it further, because it is going to say what could have happened, and what could have happened happened somewhere else in the multiverse. And by the way, we also see there a statement of how the multiverse is not this cosmological multiverse. The cosmological multiverse is sometimes invoked in order to explain why we do see, for example, the charge on an electron being what it is. If we have this so-called cosmological multiverse, it's like more like a megaverse where all the different laws of physics are instantiated out there and all the different values of the constants of nature exist out there in some way, shape or form. Then this can be an explanation for why we find ourselves in the universe that we do with the constants of nature that we do if all the others really exist in some way. That's not the multiverse that we're talking about when it's the Everettian multiverse. This is a different thing altogether, the quantum multiverse. We know that that one exists. We don't know that the higher order class of multiverse actually exists. We know that this multiverse exists because it's required by the equations. It's required by the experiments. It's the only known explanation for the experiments, the outcome of the experiments that we see. But there's no sense in which this other multiverse, in which you have all the different values possible, which is, well, it doesn't make much sense, but all the different values of the charge on an electron are out there, instantiated somewhere in some sort of higher order physical reality. So that's not something that we know. We don't know about that particular universe. It's not required by any experiment or any equation or anything like that. It's merely one hypothesis among many for trying to resolve this problem of why the laws of physics have the form that they do, why the constants of nature have the value they do. It could be God did it, it could be this megaverse, we just don't know. We've got to wait for someone to come up with a theory that is in some way testable, but we have no conception of what these theories are or how to distinguish between them. So I'll end this episode with basically the way I began it. The instant is not in time. Time is in the instant. Again, this is from the great physicist and author Julian Barbour. Barbour spends time critiquing the block universe notion that we get from general relativity, from space-time physics. But he's expanding on basically what was said by Ernst Mach, who was saying such things before Einstein was, in reference to Newtonian physics. That's what Mach was doing. The Mach family, by the way, was like the Bernoulli family was to chemistry, I suppose. Ernst was the godfather of Wolfgang Pauli, of the Pauli exclusion principle, of which I'll mention a little bit more in just a moment. And Ernst Mach was the father of Ludwig Mach, who we've implicitly talked about a lot before, because he is the inventor of the Mach-Zehnder interferometer. That's spoken about at length in my Multiverse series. But Ernst Mach, everyone knows him by name. He has achieved immortal status, I suppose, because he lives on forever in the Mach number. When a plane goes supersonic and travels at Mach 1 or Mach 2 and so on, this number is named after him. It is so named, the Mach number, named after him. But the reason why that term is useful, just a little bit of physics here, because the speed of sound changes depending upon air pressure. And that varies according to altitude. So the Mach number is different at sea level compared to 10,000 meters up, much less 100,000 meters up, which is where, spy planes or the fastest plane of all time, the fastest jet of all time, travels about 100,000 meters up, the Blackbird. So that's Mach, and Ernst Mach or Ernst Mach. Going back to time and to summarize a little bit about what we've talked about here in brief, and we will absolutely come back to this next episode, and when I speak to Sam about this, the Page-Wooters formalism or the Page-Wooters construction. And they're formalizing what is said in terms of quantum theory about time, not relativity. They explain, as Sam explains in his paper, and we've talked about briefly, that clocks are physical, and the only way that we can mark time, or the only way we can measure time. Given clocks are the only way we measure time, and all physical processes are at base quantum processes, if all clocks stopped, literally all clocks, and that includes processes in the human body and absolutely everything, but, to stop all clocks in the universe is to step outside the laws of physics. So it's not possible, and it's kind of the only point is to actually talk about this in terms of as a thought experiment, to try and illuminate our misconceptions about time. If every single physical process stopped, time would not keep running, because there is no time over and above the change that occurs. The processes in the physical universe, the clocks, which are any physical process in the universe. There's no external time that is flowing or marching on separate to the physical processes that are going on inside the universe. This, we will come to see, is illuminated by Sam, who uses what is called the Heisenberg picture of quantum mechanics, which is separate to the Schrödinger picture of quantum mechanics. Both of them are equivalent and they can be proved as such, but the Heisenberg picture makes all of this stuff more explicit because there's no need to refer to waves. So it helps when you use the Heisenberg picture, reduces the possibility of misconceptions being introduced to do with wave-particle duality. What you have is just, at this instant, you have a particular state of the universe or a state of a quantum system, and at another instant you have a different state. There's also, by the way, no action at a distance. The no action at a distance thing solves problems at the heart of quantum theory and was explained in a paper by Kuyper and Deutsch. And that was titled Everettian Relative States and the Heisenberg Picture. In that paper, they explain how entanglement really works and how all interactions are local. By local in physics, we mean no information is transmitted faster than light. This is crucial, as you hear wrongly, both in popular accounts and, also still from professional physicists who seem not to know any better, that entanglement proves that there is action at a distance, or faster than light travel, in other words. Just recall, Einstein himself didn't get it. He called this phenomenon spooky action at a distance. And because he was a realist, he would have likely appreciated Everettian quantum mechanics if he'd known about it, or if he could have met David Deutsch. Einstein was rightly struggling to make sense of things. He was a genius, but he wasn't perfect. Sometimes it takes another genius like Everett to sort things out. But, back to time, just quickly again. Heisenberg makes explicit that quantum observables are matrices and not single values. The numbers, for example, that are the observables, that describe the observables, do not commute. Kuyper makes this point well in his paper. The non-commutable property means the observable of a quantum system, like position and momentum of particles, are intimately related, and the mathematics means they cannot be known simultaneously. Non-commutable means it matters the order in which you determine the observables. Quite a remarkable property of quantum systems that is unlike anything in classical mechanics where it's trivial to know both at the same time. Classically, for a formula like P equals mv, you need to know the momentum P at the same time as the position, because v, the acceleration, is just the first derivative of the position x with respect to time. In quantum mechanics, as Kuyper explains, and we'll come back to that, following Page and Wooters, time doesn't flow. And I've talked previously about how contemplatives know this as a matter of subjective experience, but I won't go into that again now. But just to say there's a harmony with physics. There is an eternal present, if you like. The present moment is just at every point throughout the universe. So there's a sense in which there is no time, there's timelessness. There's a documentary out there, I'm got to find it again, I haven't been able to find it just now, where Barber is there, Julian Barber is there, talking about, he's holding a photograph of his office, a picture of his office. And he says that the picture, the photograph, reeks of time. The things there can only be explained, in other words, by reference to other moments. But there's no flow of anything. It's just change, then change again in discrete steps. Time is in the instant, he says. It's a Q number time, as Kuyper says. It's a stationary clock at any instant that is a different clock at the next. Nothing's changing, emphasis on the ing there. Time is just change from one discrete snapshot to the next. Change is not because time flows, but because a clock increments. The instant is not in time because there is no external time. Time is in the present. The instants are fundamental. Time is a word labeling a fiction that we've all agreed on. There is no time in a real sense. There is only the eternal now. Physics says so objectively, and, okay, contemplatives demonstrate this to themselves subjectively. Anyone can prove this to themselves with sufficient attention as well. Either go the physics route and prove it to yourself by reading and listening to the experts, or prove it to yourself by paying attention to now via meditation or mindfulness or whatever method. In both cases, whether it's physics or contemplation, you'll end up with an objective fact of the matter. There just is the instant. It's where you think you find time. But there is no time when you look closely enough, especially at the physics. As I said last time, until next time, bye-bye. If you enjoyed this episode or you found any value in it, please go to my website, www.bretthall.org, and subscribe to my Patreon. Or you can contribute to this ongoing project via PayPal, if you like. Any and all donations of any amount whatsoever are deeply appreciated. Again, until next time, bye-bye.